Welcome back to Applied Mathematics. In this video, we're going to be digging into some properties of geometry with a discussion of lines and angles. Let me get my head out of the way, and we're going to start with, well, I'm sorry, but we have to start with a little bit of notation and vocabulary. So, if we have a couple of points, A and B here, if I want the line through A and B, I'm going to denote that as AB with a double-headed arrow over it. And my points have gotten a little bit too close to my discussion, so let's get them out of the way so that I can draw the line through AB. Generally speaking, a line which is infinitely long and continues onward in both directions forever is not all that interesting in geometry because it's something that cannot be measured. So for geometric analysis, we more often are going to worry about a segment. And if I want to talk about the segment between points A and B, I will again denote it using those letters A and B. This time I will put a bar over those that does not have arrows on it. And the segment is just the portion of the line between those 2 points. The reason that a segment is so valuable is because a segment has a measurable length. And so we're often going to be looking at the length of line segment AB. And we will denote that using just the letters with no bar. And right here immediately, we come to one of the first big issues that students have in the study of geometry. The two characters, A and B together, is a single measurement. It's not two separate variables, it's one variable with a two-letter name. That is going to confuse you at some point, and I want you to make a note of it in a place that you are going to very easily be able to reference it, because as you look back in your notes trying to figure out what's going on, you want to be able to find this quickly. I cannot tell you the number of times in my own career as a student where I've been completely puzzled by what was happening in an equation, only to go back and realize, 20 minutes into my scratching my head, oh, AB is the length of a line segment. It's not two variables, A and B. It feels obvious, but it is a mistake because we are so accustomed to dealing with one-letter variable names for almost everything. The last shape that I want to talk about is a ray. A ray is kind of a cross between a line and a line segment. So if I want to talk about ray AB, I might put a single-headed arrow over top of those. And that would be the portion of the line starting at A, going through B, and continuing on indefinitely. We're almost never going to denote rays or talk about rays, but they do serve one incredibly important purpose. And that purpose is talking about angles. If you have two rays with the same terminal point, in this case, I have named points P, Q, and R, and rays, let's try that a little bit more carefully, ray PQ and ray PR. The angle between those two rays we can denote using the angle symbol, which kind of looks like a capital L that's fallen down a little bit. And then the ordering here, well, you have two options. You come in through Q, turn around at P, and go out at R. Or you come in through R, turn around at P, and go out at Q. Either way, you can talk about the angle by naming those 3 points. In a picture like this one, the angle is unambiguous, and just calling it angle P is perfectly fine. But speaking in general, we're not going to be looking at such clear pictures. We are usually going to be looking at a situation where the intersection is in fact two lines. So if you want to talk about the angle at point P, you might be talking about any one of those 4 angles. But in fact, that notation is exactly what we can do. I can name these angle 1, angle 2, angle 3, and angle 4 because writing 3 letters to describe an angle is just entirely too much work. The one thing that I want to stress here, these numbers are labels, they are not measurements. You can't add angle 1 plus angle 2 to get angle 3 or anything like that. I try to think about them the same way I think about subscripts. Right? If you have a bunch of things you want to call x, you might subscript them and call them x1, x2, x3, and x4, the x coordinates of 4 points in the coordinate plane. The numbers here are serving the same purpose even though they aren't being written as subscripts. But now that we have these 4 angles in this picture, I can start talking a little bit about some of the vocabulary we can use to describe the relationships between angles. In this picture, there are 2 types of relationships. Supplementary angles come together to form a straight line. For example, in this picture, angles 1 and 2 are supplementary angles. Likewise, angle 1 and 3, angle 2 and angle 4, and then angle 3 and angle 4. There are 4 pairs of supplementary angles in this picture. The only remaining combinations of angles are angle 1 and angle 4, as well as angle 2 and angle 3. The picture here of 1 and 4, I think, highlights a little bit more clearly where the name comes from, but it is going to be just as true of angles 2 and 3. This picture is what we refer to as vertical angles. And the nice property of vertical angles is that the measure of vertical angles is always equal. You may have at some point in the past come across this fact, and you may have come across it in a case where your instructor wanted to write out the proof of that. For the sake of time, I'm not going to write out the proof formally because, well, that's not something that's very important in this course, but I do want to talk through the proof because I think this is a really nice place where we can stop and take a moment to really understand that the rules of mathematics are not arbitrary. They follow from the rules that we've already established. We basically start with what is 1 plus 1, and everything else falls into place from there. But if we look at angles 2 and 3, I know that angle 2 paired with angle 1 form a straight line. A straight line has a measure of 180 degrees. Likewise, angles 1 and 3 form a straight line, so if you add those two angles together, you also get 180 degrees. Well, just following along from that, if the measure of angle 1 plus the measure of angle 2 is 180 degrees, and the measure of angle 1 plus the measure of angle 3 is 180 degrees, then it must be the case that if we add measure of angle 1 plus measure of angle 2, we get the measure of angle 1 plus the measure of angle 3. Right? If they're both equal to 180 degrees, they're equal to each other. And then I can cross out the measure of angle 1 from both sides of that equation and get that the measure of angle 2 is equal to the measure of angle 3. The reason that mathematicians love giving arguments like this is because I said absolutely nothing about these angles except that we have this picture with 4 angles formed by 2 straight lines intersecting each other. And just with that, we have everything we need in order to start playing this matching game. All right. Onward. The next picture, a phrase that has struck fear into the hearts of high school students for decades. Two parallel lines cut by a transversal. That just sounds terrifying. But once you learn what these words mean, it's actually really straightforward. So first, let's draw a couple of parallel lines. All right, those two lines look more or less parallel. We already know that parallel lines means that they continue the same distance apart from each other their entire journey, and they never come closer, they never intersect, they never get further apart. Let's go ahead and name these lines. How about L and M? To denote that two lines are parallel, the symbol is an equal sign turned on its side. All right, so that part is easy, two parallel lines. Cut by a transversal. Why do we say cut by? I don't know. That is terminology that has stuck around since, honestly, probably since the ancient Greek times. To be cut by a transversal means simply that there is some other line in the picture. This other line is not parallel to the two lines we started with. That's it. That's all it means. And because we're talking specifically about being cut by this transversal, that means that we can clearly see in our picture the place where the transversal intersects each of the two parallel lines. Why do we have to make it sound so intimidating? I really wish I knew. I really wish I could give you a good answer for that, but this is the language that mathematicians have used for time untold. Let's put some names on these angles. I guess I've got angles 1, 2, 3, 4, 5, 6, 7, and 8 here. That's really small. Let's make this bigger. There we go. Now we can actually read these labels. So the idea here is if you look at those two boxes, the picture of where the transversal intersects each of the two parallel lines looks like the same picture. And so that's where the terminology of corresponding angles comes from. Angle 1 and angle 5 are both at the top. Likewise, the way I've drawn this out, angles 2 and 6, angles 3 and 7, and angles 4 and 8. Corresponding angles have equal measure. That's actually, in the formal study of geometry, the definition of parallel lines. Two lines are parallel if, when cut by a transversal, corresponding angles have equal measure. With that fact, along with what we've talked about previously about a single intersection point, you actually have everything that you need in order to analyze these angles. But I do want to at least quickly mention some other vocabulary. You may or may not remember seeing this vocabulary in a previous mathematics course. If you don't remember it, it's fine. But if you have a vague recollection of this, and this sparks and helps you remember it, it might make your life easier moving forward. The alternate interior angles are angles 4 and 5, and angles 3 and 6. If you don't remember that name, you can get there in a two-step process. Angles 1 and 5 are corresponding, so they have equal measure. Angles 1 and 4 are vertical, so they have equal measure, which means that angle 4 and angle 5 are both equal to angle 1, and the only way that can happen is if they're equal to each other. There is also the terminology of alternate exterior angles, and those are going to be, in this case, angles 1 and 8, and angles 2 and 7. The other possible relationships between 1 and 7, 2 and 8, 3 and 5, 4 and 6 are called same side exterior or same side interior, and those are all relationships of supplementary angles. That terminology exists. For what we're going to be doing, it's almost never useful, but it does exist, and so I wanted to at least make a quick mention of it. The last thing that I want to talk about in this video is the rule that says given three parallel lines cut by two transversals, the lengths of corresponding segments are in proportion. And once again, this should seem very obtuse, very difficult to understand at first glance. So let me draw as best I can the picture that we're talking about here. So here I've got three parallel lines. Let's call them L, M, and N. And then let's put in two transversals. Here's T, and there's S. The two transversals each get segmented in a couple of places. The segments of the two transversals between L and M, and the segments of the two transversals between M and N. Let's label a couple of these points. Right, the points on transversal T are A, B, and C, and the points on transversal S are X, Y, and Z. What this statement is saying is that if you take the ratio of the lengths of those segments on transversal T, AB over BC, and you take the ratio of the segments in the same order on segment S, XY and YZ, those ratios are going to be equal. All right. Before I get into why this is useful, I want to spend a little bit of time looking at the mechanics of setting this proportion up, because setting proportions up is almost always where the challenge comes in. All right, that's behind my head in a way that I'm not going to find useful, so let's just move things around a bit. That is the reason that I use a digital touchscreen. All right. So, whenever you're setting up a proportion, the thing to keep in mind is that rows and columns always have to match. And the way I set this up is the columns match with the individual lines. So the fraction here is all segments on transversal T. The fraction here is all segments on transversal S. That matching is a key part of the process. And then the rows. Why am I looking here? All I see in my room is a green screen. The rows need to match. AB and XY, those are both the segments between L and M in my picture. And on the bottom, BC and YZ, those are both the segments between M and N in my picture. So that's the way that I set things up to make sure that everything is going to match up and everything is going to work out when I set up this proportion. Now, why is this useful? Unfortunately, I wasn't able to source videos of these things. I'm going to work on correcting that in the future. But if you've ever seen a reduction or enlargement machine, where you trace an object with an arm, and then that arm swings around to trace the exact same thing on a workpiece, either at a larger scale or a smaller scale. You set that up using this. You set up two arms that are between two parallels that will be able to move around and trace the thing that you're working on. And then you have another set of two parallels that the arms are connected to that force them to swing out in different directions. And that process of ensuring that those lengths stay in proportion is what allows you to scale the object you're working at in the same proportion. Another really nice trick that if you've not seen and you are doing this kind of work is really going to save you some time. If you've ever needed to find the center of a workpiece and you've tried to measure as close to perpendicularly as possible, you write down the measurement of the width of the piece, you grab out your calculator, you divide by 2, and then you very carefully measure out that halfway point to mark down your center. That absolutely works, but you don't have to measure in the most perpendicular sense. You can measure at a weird angle. And measuring at a weird angle is useful because you can skew your ruler so that, say, you can get the ruler to go across 6 inches. Well, half of 6 inches is 3 inches. That's easy. You don't need to grab a calculator. You don't need to do much of any work in order to find that center point. So if you can skew your angle and find a nice number to work with, it will still give you the center of the workpiece, and it doesn't require the use of a calculator. All right, I think that's enough for this video. So I'll wrap up with that. As always, thank you for watching, and I'll see you in the next one.